In this lesson, we are just gonna go over the chapter 18. But before starting the chapter 18, we will just go the end of the chapter 17 and just review these two tables. In the first table, table 17.81 is defined the mass and molar fluxes, all the definition and all the formulas. Here we can find, for example, molar flux for species alpha. Here is molar big N, and mass flux of species alpha defined by this form. All other things you can find here. Then we will go to table 17.82 is give the binary diffusions or different forms of fluxes and gradients. For example, in here it shows again for the total or combined mass flux of the species A, gradient is del WA is defined here, and you can find the form here, or molar flux combined or total molar flux defined here, gradient again, del XA is the molar fraction of the species A. You see is defined by this form by the binary system. Binary system in your system is has two species A plus B. Diffusion is happening through the A through the B and B through the A. We call this binary system. As comes this forms in second form, we know from this is the diffusion transport because of the molecular transport, and the first term is defined the convective transport because of the bulk movement of the species. Again, in this form is same as that one, but this form comes from here. Why? Because we define, if you remember, V star is the average molar velocity is defined like this. Is the number of species go from I from the 1 to n. We can write Ci species I molar concentration multiplied by the Vi. Vi is the velocity of the species I. It is not the molecular velocity, but it's the average velocity of the species I, and divided by the total concentration C. We can write that one is a 1 to n. We can write this xa and again sorry xi and vi. Anyway, so in here, if we take this form here, we write ca, and if we just put here for the two species I and B, you can write that one, that form, ca multiplied by va plus cb multiplied by vb divided by C, total concentrations. We know from the definition of the total molar flux, this gives us the big Na from the above table, and this gives the Nb. If you take this out here, then Ca divided by C is given as a result of Xa, and we have obtained just that from this comes from that definition, so on. Now we can go in chapter 18. In chapter 18, in here, we are just gonna go and review some steady state diffusion problems, and we can just learn, we just try to learn how to formulate this problem by the shell mass balance approach. Actually, in the mass balance is made over the thin shell perpendicular to the direction of the mass transport. For example, think about any system. Let's say you have some shell balance like this, just transport is happening in this direction. We can call this the shell. Actually, we can write this in the z direction, z plus delta z. That's mean just the thickness of this shell is, we can write just delta z. It's very small, so we can make this delta z approach to 0 for the limit. Then we can obtain the differential equation for the system. We call this the shell mass balance. Anyway, then later we will obtain some differential equation here. Then we can take this definition from here, the total molar flux definition, and insert to our differential equations, and then using the boundary condition we will solve our differential equation and obtain the species molar concentration profile or molar fraction profiles along all the system anyway. So in here, in this chapter, we are gonna use mostly this definition of the Na in the z direction in the perpendicular the mass flux. Actually, it is between the flux and the concentration gradient, the direction of the mass transport. We call this perpendicular. The shell balance is going to be perpendicular. Like here, the direction of the mass transport. We know from the chapter 17, we can define the combine our total molar flux by this form, this diffusion term, because of the species molecular transport, and the second one convective transport because of the species bulk movement. So um, so just go and view here. In here, we just need to define for the system's reaction term. In here, for the homogeneous reaction, let's say you have the system. Your system is the homogeneous system, and the reaction happening inside of the homogeneous system. Then we can call this homogeneous reaction. The molar rate of production of species A may be given the expression of the form del 1 is give the production of the species A mole per meter cube per second actually, or centimeter cube or per second. Anyways, it doesn't matter, it's all the same. See here concentration of the species A is moles per volume. The index N is indicate the order of the reaction. We know from the reaction class. If this is the first order reaction, if the N is the 1, then our reaction rate takes the form unit of the 1 over S. But at the same times, we can have another type of the system we call this heterogeneous reaction. Let's say you have some catalysis is solid form and some gas is flowing around the catalyst and give the reaction. We call this kind of system like a heterogeneous system. Then we have to define the reaction rate, the total molar flux at the surface of the catalyst is given by this form, the reaction form, and actually the definition of this form is give the effectiveness factor of the catalyst. And anyway, we will later, we're gonna just go and go review these concepts again. In here, the NAZ we know from the molar flux is moles per centimeter square per seconds per area, and Ca again is here the concentration, and here is the rate constant is given, the double prime is given centimeter per second. Okay, this is the difference between two system, and rate expression is changes respective system or homogeneous or heterogeneous. So anyway, now here in this section 18.1 we will go and check some shell mass balance and boundary condition. We know from any system, let's say we know from any system like that, if we define some system boundaries like this, if some mass flowing from here, so the rate of mass of the A in this system like this, and rate of the mass of A out from your system, we call this system our control volume, and these are the control surface. From the bottom, the A is enter the system. From the top surface, A is goes out from our system. So rate of production of the A by the homogeneous reaction is going to be equal to 0, because why? We are just in this chapter consider the steady state operations, but it's a steady state example. That's why this right side term is going to be 0 anyway. So if you go and continue our discussion, we can define some definition here. The concentration at the surface can be specified. For example, XA is going to be equal to XA0, and at the same manner we can define the mass flux at the surface can be defined NAZ is equal to NA0. Then if the diffusion is happening is in a solid, it may then happen the solid to surface substance A is lost to a surrounding stream according to relation. This relation is Na0 is going to be equal to Kc is Ca0 minus Cab. Ca0 here is the species A concentration at the surface, and Cab species A concentration in the bulk, and Kc is the mass transfer coefficient. So anyway, okay. The rate of chemical reaction at the surface can be specified by this form. Na0 is going to be equal to K1 double prime Ca0 we defined for the heterogeneous systems. We need to know this for different type of definitions. So our first example is going to be about diffusion through the stagnant gas film. Just consider this kind of system. You have some liquid here. The level of the liquid is Z is equal to Z1, and we assume is this problem, the level of the liquid doesn't change, so we keep the liquid level in here always constant at the Z equal to Z1. Then so evaporation of the liquids happen, so it's produced just the gas of A. At the top of the liquid we have the species gas B. We consider gas B as the stagnant. That's mean the gas B is not soluble inside of our system. So in here, let's say we have the gas B, but the gas B is not soluble through the liquid. Then that's why we can define the gas B as a stagnant. So in the stagnant B here, just the transport of A is happening from starting from the surface of the liquid or through this system. We define our system starting from the Z is equal to Z1 is equals to Z equal to Z2, and problem is asking to just find the species A and species B concentration profiles along this length for species A and species B. Actually, if you find the concentration of the species A, like XA, from starting from the Z1 to Z2, then we can obtain similarly species B concentration by this form, because 1 minus XA is going to give this species B concentration or molar fraction or concentration profile along this length. Anyway, so this is going to be our system from the definition of the problem. Also, this problem is defined as a steady state diffusion of the A through the stagnant B, the liquid vapor interface, maintained at the fixed positions. So anyway, so from here, from here, we just beginning of this chapter, we define this formula for the binary systems. So we can take this. We are gonna use this formula for this system. Just writing our formula again here. Species A here, NaZ in the Z direction. Diffusion is just happened minus C DAB XA DZ. It's going to be plus XA and NaZ plus NBZ. This is going to be our total flux, but what we know in this system, the species B is just stagnant, then this is going to be zero, because the total flux of the species B through the species A is going to be zero. That's why from here we can just obtain this form from here. Actually, let me write again how we come from here. Again, sorry. Then this NaZ is going to be a Q minus C DAB. From here dXA dZ plus here XA NA. If you take this NA from here, this side actually, and common parenthesis NaZ, we are going to obtain from here 1 minus xa is going to be equal that 1 minus c dab xa, and this anyway. If we take this from here, leave alone this naz, then we obtain minus c dab 1 minus xa dxa. So this is going to be our final relation for the species A through the positive y directions. So from anyway for this system, let's say we have, you see from here we have some uh, from here shell balance. We just obtain here very tiny, very small, had very small thickness delta z, and we can write the shell balance. So species A total flood in the z direction from here, which is not here. In the this we know from the per area we can multiply this the s is the cross section area of this tube from here. It's going to be minus s multiply na z plus delta z. This is actually going to be equal to 0. So this is our shell balance here. We can write shell balance for the system. So like here, then if we divided these terms by s multiplied by delta z, let's say we divided this, the right side is equal to 0, and then if we take the delta z approach to 0 and we take the limits as approach to delta z 0, then we can obtain differential equation like minus dnaz divided dz is going to be equal to 0. So this is going to be our differential equations, just define our system here. But what we know, what is our total or combined molar flux, this is going to be equal to that one. Then if we take that definition and insert here, we can just obtain that form. Taking minus sign other side is going to be 0, and we will have that form here. Just the dxa over dz, how the our species A molar fractions change respect to z actually, and these are, we know from the our system, c is the total concentration, and dab is the diffusivity between binary system A and B. This term is going to be actually constant, and we can take this out from here, and if we take this out, and we can, if you take this right side, is going to be 0, and finally we will have that form here. Now how can we solve that one? This is the second order differential equations we know from the mathematics, and we can integrate this 2 times and we can obtain 2 integrate constant. The first integration is give the constant c1. If we integrate in the second time, at the left side we obtain minus ln 1 minus xa and c1 multiplied by z and plus c2. You see we have 2 constant comes from integration. If we again define this c1 by minus ln k1 and c2 minus ln k2, and we can write this form as a 1 minus xa is going to be equal to k1 multiplied by k2 from the new definition. So in here the k1 and k2 are the constant. Since this is the second order differential equations, we need to define 2 boundary conditions for the system to find our 2 constants. Our first boundary condition is going to be z equal to z1. At that one, at the z is equal to z1 is going to be in the surface of the liquid. We can define this xa is going to be xa1. Second boundary condition is going to be z is equal to z2 is going to be xa is going to be xa2. So anyway, so just like as here we define 2 boundary conditions. Now, if we solve this equation for two boundary condition, finally we can obtain this final solution. So this give 1 minus xa species A concentration profile between Z1 and Z2. Actually, the xp can be defined from here. 1 minus xa is going to be give the gradient or concentration gradient of the species B. From here, from here, um, we can just replace the 1 minus xa by the xp. Finally, we can obtain from here the concentration gradient xp's average can be written by this form. In here, the average value of the xp is just the logarithmic mean, and xb ln just defined here. You see from here. So if you continue from here, the rate of the mass transfer at the liquid gas interface, at that interface again, if you just go and check from here, just at this surface, this liquid and the gas interface, we call this interface, we can just write the rate of mass transfer by NAZ, Z is equal to Z1, and we can write that one minus CDAB1 minus XA1, because as we said before, at the surface, we define our XA as a XA1, and this is going to be the XA divided by DZ. This is going to be Z equal to Z1. We can write this in terms of B. If we exchange 1 minus XA1 is equal to XP1, we can write this form. Now later, again, we can, if we solve this, if we solve this, that one, from here, from the z is goes from the z1 to z2, we can just write that one, integration, differentiation, and we can write the differentiation of this xp from here. If you remember from here, xp, we can write that form. So this is going to be give us actually the rate of mass transfer, or the total molar flux at the interface, can be written by this form. So now the combining the equations from here, 13 and the 14, this equations from here and this equation combination of this finally gives this result. So this expression gives the evaporation rate in terms of the characteristic driving force XA1 and XA2. So anyway, so this is our solution actually for this binary system, steady state system from here actually. But another type of system can be defined. For example, in the first example, we just set this liquid level is the constant, but another type of problem, maybe the liquid level can not be always in the same level. For example, when the time goes and when the liquid is evaporate, then the level of the liquid is going to be reduced during the time. This is going to be our another system actually from here. So we call this diffusion with a moving interface. This time is the interface you see from this liquid level is just reduced because of the evaporation. So we can just define actually here. We can just define here. Let's write liquid. Liquid, we can define liquid masses as a m. From here, m is just rho multiplied by s, and the z. Actually, if I want to find the mass of this liquid, rho is going to be kilogram per meter cube. It's going to be meters square, and this is going to be meters square, and then we can find from this formula the total mass of the liquids from here. So then we can write dm over dt is going to be give us the change, total mass change of the liquid inside of our system, our control volume. Actually, if I write this form in rho as z over dt, the rho is going to be constant for the liquid, and s is the cross-sectional area is going to be constant. Then we can take this out, and rho s we can write just dz over dt. So this is going to give us the height change of the liquid, z change the liquid with respect to time. So as we can write here, because this is the minus sign, because we are losing the mass because of the evaporation, and this is going to be actually equal to our solution from in the first section, because we find our NNZ at the z is equal to z1 at the interface. This gives the rate of the mass loss at the interface, but this just give kilogram per meter square multiplied by s. If we multiply by this s, we can find this is going to meter square kilogram per second. This is going to be equal to the left side. So this is going to be uh, our actually relation, how the mass of the liquid change inside of system or other world, how the z is changing respect to time. So then if you take this form, actually, and if we take the dt over here, and if we take this because the z1 this time here is not the constant from the solution, just we are using this solution we obtain here. Z2 minus z1 in the first example was the constant z1, but this time our z1 is changed respective time. So take this here under the dz1, and take the integrate. If we integrate this from the 0 to hash, actually uh, what is the hash is small hash here, h here, actually respect time, z1 at the time 0 minus z1 at the time any time is give the a small h. A big H is going to give the z2 minus z1 at the time 0 actually. So we can write here inside of here uh, h big H plus small h, and we can define dh. If we integrate this left side and right side from the time 0 to t, we can obtain this final form here. This is give us the uh, uh, actually height change of the liquid in this system and respect to time. So this is our another example. What we have seen here, we have seen two examples: the constant liquid level example, and the another one moving interface example. These are the two examples we have seen just here. Okay, if we just go another example here, actually these examples talks about diffusion through the non-isothermal spherical film. Let's consider any spherical system like here has the radius of r. Um, Now the problem part A says derive the expression for the diffusion through the spherical shell that are similar to the first example. The systems under consideration is the shown in the figure here. Actually, our system is going to be like this. This is the core here. The R sphere has the radius of the R1, and in here we just write here this thickness here going to be our shell, and we can define this R2 actually. And this is the not isothermal system. This is just non-isothermal systems, and we can define our temperature difference between. We can find the temperature T2 equal T1 multiply R2 divided R1 is the n power, and the temperature is here, just here. You see the core has the temperature of the T1. So anyway, the first part says just derives the derived diffusion expression for diffusion through the system. For the steady state mass balance, if you write for example, if you consider this the shell balance, we can write from here just for very similar the first example. Species A goes actually through the let's write NA R square from here and minus R square NA R very small of the change of the in the R is going to be equal to 0 from here. If it divided let's say write the S cross-section area for the transport is happening. If you divide the both side by the S by the delta R and take the limits delta R is approached to 0, then we can obtain this differential form for this differential form for this system. Actually, this is the R differential form here. Now, from here, as we know from the first part, in here, what is our system? You see, just the gas A is diffusion is happening through the sphere. So that's mean the species B is stagnant. So then we can write species A is go through the R direction, can be written again minus C DAB. Actually, the XA dr is going to be XA NAR plus NBR. This term is going to be again 0 because not the species B diffusion happens through the A. Then from here we can again obtain NRR is going to be equal minus C DAB 1 minus XA DXA dr. So this is going to be our definition of the total or combined molar flux. Then we can just take this and insert here in the differential equations, similar to the first example. If we insert here, we obtain that form, and then we can take again the C, the AB is constant out, and from here we just left d over dr. R square is 1 over XA, the XA divided by dr is going to be equal to 0. And from here, again, if we obtain our boundary conditions at the, you see the interface, at the interface we can define at the interface here when the R is equal to R1, R XA is going to be equal R XA1, similar to first exam at the interface from here. When the R is equal to R2 in the shell balance, R in the system, the gas film, we call this gas film. This is not the actually shell balance, this is the gas film. Just write the here very small shell balance here. Actually, this we call this delta R, but this is the gas film, not the shell balance. Again, sorry again for that. So if you continue, then Rxa is going to be Xa2 at this in here. This is the Xa1, Xa2. Then this is going to be our two boundary condition. If we solve this problem again, similar to first example, and for example, first example, we can obtain the concentration profile for the constant temperature for the XA is going to be that form. So this is actually our this form our concentration uh, concentration profile for the constant temperature. You see, at the interface from here, if you remember the core and the gas film at the interface, this is the solid gas interface. The the total or combined flux of the species A can be written by this form when the R is equal to R1. We define NAR and multiply by the area, by the cross-sectional area. We know the cross-sectional area 4 pi r square from here, and we can obtain this form. So this is the give us the total combined rate of mass through the interface, and this is going to be kilogram sorry, this is going to be mole per second actually, and this term is gives the mole per meters square multiplied by time, and this is the area anyway. So this is the part A of the problem. In the part B, actually in the part B, asking here, so say just consider the non-isothermal film. So the temperature is changed by this form, where the T1 is the temperature at the R is equal to R1. Assume the rough approximation that the AB varies as the 3/2 power at the temperature. So we can obtain diffusivity of the binary system when the temperature change. As we know from the chapter 17, diffusivities of the systems can be changed respected pressure, respective temperature, and respective composition. So this gives us the diffusivities of the binary system diffusivity for the different temperatures. So from here, we just take this definition and just write here. So we just use the same expression here as we obtain here. There's that expression from in the first A, but this time you see our DAB is not the constant. We cannot take this out. We can write. We have to write the definition of the DAB like here. Then take this DAB one here and insert inside of our differential equations. Then take this differential integrate and integration, and then the solution of for the two boundary conditions finally, and we can obtain total mass transfer at the interface by this form. So although this is also another um, form of systems, and what did we learn in here? If your system is not the isothermal, that's mean your diffusivity can be changed respect to temperature. We can define some diffusivity change by this form and inserting inside of differential equation and integrating 2 times, obtain 2 constant and writing our boundary conditions same as part A. Then we can solve this for this boundary condition, and we can write the actually total flux at the interface. So this is our this is going to be our first video or first lesson for chapter 18, and we will have another video for the chapter 18 as a second part, and see you in the second part of the chapter 18 actually. So